I pass over to you. You can introduce the speaker.
Sure. So welcome everyone. Thank you for being here. And it's my pleasure to introduce Professor Dijana Ilišević, who is the speaker for today's colloquium. Professor Ilišević did her PhD from University of Zagreb, and now she is a full professor at the University of Zagreb. And her research interest lies in functional analysis, operator theory, functional equations, and interplay between algebra and analysis. She has authored numerous papers. She has given conference talks all over the world. She is serving in the editorial capacity for many reputed journals. So without further ado, I pass the baton to Professor Ilišević. Professor Ilišević, welcome to our department.
Thank you very much. I would like to thank Sudeshna for inviting me to give this talk here in India, unfortunately only virtually, but I'm happy to have at least this kind of opportunity to present my research work. I'm going to talk about isometries. I hope that you can see my slides. The word isometry means having equal measurement. It comes from the Greek language. So it is okay to define an isometry whenever we have distance, that is in metric spaces. An isometry is a map between metric spaces that preserves distance between elements. But throughout this talk, we shall be interested in isometries between norm spaces. More precisely, we shall be interested in surjective linear isometries on Banach spaces. And why surjective, we shall see during this talk. The beginnings of the study of the structure of linear isometries on Banach spaces coincide with the very beginnings of the Banach space theory. That is with the Banach's book, which was published in 1932. However, this is still a very active area of research. And one of the main problems is to give explicit description of isometries on a particular space. So we shall start with this problem, but I would like to mention that there are two excellent books written by Professors Richard Fleming and late James Jamieson on isometries on Banach spaces, which I recommend for those interested in isometries. We start with the simplest Banach space, that is with a finite dimensional real or complex vector space in which the norm is induced by the inner product. That is, in which the norm is the so-called Frobenius norm. It is known that linear isometries on this space are precisely unitary operators in the complex case and orthogonal operators in the real case. And from now on, we shall be interested only in those Banach spaces equipped with the norm which is not induced by the inner product norm. The very first result on the structure of linear isometries on a particular space is this one by Schur from 1925 concerning linear isometries on n-by-n complex matrices equipped with the spectral, that is, operator norm. Linear isometries of this space have one of the following forms: X maps to UXV, or X maps to UX transposed V for some unitary matrices U and V. We can consider more general norms, the so-called unitarily invariant norms on n-by-n real or complex matrices. The norm on this matrix space is called a unitarily invariant norm if the norm of UXV is equal to the norm of X for all unitary or orthogonal in the real case matrices U and V and all X. And clearly, maps of this form, X maps to UXV, are isometries for this space. But not the only ones, because we also have isometries of the form X maps to UX transposed V. But these two are the only types of isometries, unless we have 4x4 real matrices, when we have some, I would say, more exotic isometry like this one. We can also study n-by-n complex symmetric matrices and n-by-n complex or real skew-symmetric matrices equipped with the so-called unitary congruence invariant norm. These are the norms satisfying that the norm of U transposed XU is the norm of X for all unitary or orthogonal matrices U and all X from the space of symmetric or skew-symmetric matrices. Again, clearly, maps of this form, X maps to U transposed XU, are isometries of this space. In the case of n-by-n complex symmetric matrices, these are the only isometries. The same holds that these are the only isometries on n-by-n complex skew-symmetric matrices unless n is 4. If n is 4, again we have a more exotic isometry. This isometry maps gamma to the matrix gamma, maps X to the matrix gamma of X, which is obtained from X by interchanging its 1, 4 and 2, 3 entries and interchanging its 4, 1 and 3 entries accordingly. In the case of n-by-n real skew-symmetric matrices, there are also isometries of the form X maps to U transposed X transposed U. They don't appear in the list of isometries for in the complex case, because it is obvious that we can replace U by imaginary unit times U and get this type of isometries as well, because we are dealing with skew-symmetric matrices. We can also study some infinite dimensional spaces, like C0 of omega, the algebra of all continuous complex valued functions on a locally compact Hausdorff space omega vanishing at infinity. Isometries of this space, this time we assume surjective linear isometries because now we are in infinite dimensions, are in fact weighted composition operators. More precisely, a surjective linear isometry T maps the function f to T of f that sends omega to U of omega times f of phi of omega, where phi is a homomorphism between Hausdorff spaces and U is a continuous function on the Hausdorff space taking values in the unit circle. This theorem is known as the Banach-Stone theorem, because the first Banach's version of this theorem appeared in his book in 1932 for real-valued functions on compact metric spaces. And this result was extended by Stone 5 years later for real-valued functions on compact Hausdorff spaces. There are also some other spaces in which surjective linear isometries are weighted composition operators, and we refer to the results of that flavor as the Banach-Stone type theorems. Now we can go to more general Banach spaces, like C-star algebras. A C-star algebra is a complex Banach star algebra A, in which the norm satisfies the so-called C-star axiom. The norm of A star A is equal to the norm of A squared for all A in A. The simplest example of a C-star algebra is the C-star algebra, the field of complex numbers, with the absolute value as the norm. Then we have B of H, all bounded linear operators on a complex Hilbert space H, or K of H, all compact operators on H. B of H is an example of a unital C-star algebra, while K of H is an example of a non-unital C-star algebra. And we also have commutative C-star algebras. C of omega, all continuous complex valued functions on a compact Hausdorff space omega, and C naught of omega, already mentioned, space of all continuous complex valued functions on a locally compact Hausdorff space omega that vanish at infinity. We know the structure of surjective linear isometries of C naught of omega, but what about surjective linear isometries on an arbitrary C-star algebra? This question was answered by Caddison in 1951. If we have two unital C-star algebras, then any surjective linear isometry between these C-star algebras is a Jordan star isomorphism multiplied from the left by a unitary element. And this result was extended to general C-star algebras, not necessarily unital ones, by Peterson and Sinclair 20 years later. And it is a result of the same type, again, a Jordan star isomorphism multiplied by a unitary from the left, but here we cannot work with unitaries in a C-star algebra, but we have a unitary operator on a C-star algebra. And for those that know maybe more about C-star algebras, we can say that this unitary U is 1/2 of the so-called double centralizer, which can be also considered as a multiplier of a C-star algebra. And in the unital case, this unitary operator is the left multiplication operator by some unitary elements. And in that case, the corresponding V is the corresponding right multiplication operator. This result can be specialized to B of H, because it is known that on B of H, Jordan star isomorphisms have the form X maps to V star XV, or X maps to V star X transposed V. And if we multiply it from the left by some unitary, we get that these two types of isometries appear as surjective linear isometries on B of H. X maps to UXV, or X maps to UX transposed V. Again, as in the matrix case, as proved by Schur. We can go to more abstract structures like JB star triples, for example. I like JB star triples because, as we are about to see, there is a very nice description of isometries on this space. But first, let us see the definition of a JB star triple. It is a complex Banach space A, together with the continuous triple product on A, which is linear in the outer and conjugate linear in the inner variable, which is symmetric in the outer variables. And for any x in A, the operator delta of x is defined on A by delta of x on Y, is the triple product of x, x, and y is Hermitian with non-negative spectrum. Furthermore, the following main identity holds, as stated in 4. And finally, for every x in A, the norm of the triple product of x, x, and x is equal to the norm of x cubed. Some examples of JB star triples are complex Hilbert spaces, then also C-star algebras, symmetric operators, and antisymmetric or skew-symmetric operators. These three structures, C-star algebras, S of H and A of H, become JB star triples with respect to the same triple product, which is given as 1/2 of x y star z plus z y star x. There are, of course, more exotic examples of JB star triples, but these are going to be of interest in this talk. And here we have this nice result on the structure of surjective linear isometries on a JB star triple. Every such isometry preserves the triple product, which means that it satisfies this functional equation. The converse also holds, namely any bijective linear map satisfying this equation must be a surjective linear isometry. And if A is a C-star algebra, we can write it in a different way using the formula for the triple product in a C-star algebra. And this is the equation that we get. Let us note that every Jordan star isomorphism is a Jordan triple isomorphism. And also if we multiply it from the left by a unitary, it is clear then it satisfies this functional equation. But we already know the structure of surjective linear isometries on a C-star algebra. But what we didn't know was the structure of surjective linear isometries on symmetric and skew-symmetric antisymmetric operators. Since these two structures become JB star triples with respect to the same triple product as C-star algebras, we have the same functional equation here. But what we need is an explicit formula for such T. And it turns out that such T must be of the form X maps to UX U transposed. In other words, any surjective linear isometry on symmetric or antisymmetric operators must be of the form X maps to UX U transposed for some unitary U in B of H. We can also mention a minimal norm ideal. You can think of a minimal norm ideal as a Schatten P class, but do not think of it as the Hilbert-Schmidt class because, as I said, we are not interested in the norms that come from the inner product. A minimal norm ideal consists of a two-sided proper ideal I in B of H, together with a norm on I, such that the set of all finite rank operators on H is dense in I. This norm on I coincides with the operator norm on rank 1 operators, and it is also a unitarily invariant norm. If I is a minimal norm ideal, which is not the Hilbert-Schmidt class, then every surjective linear isometry on I has the form, again, X maps to UXV or X maps to UX transposed V for some unitary operators U and V in B of H. And now we are ready to define a class of operators that are very closely connected with isometries. This is the class of Hermitian operators on a complex Banach space. A bounded linear operator T on a complex Banach space X is said to be Hermitian if E on I phi T, I is the imaginary unit, is an isometry for all real numbers phi. There are spaces admitting only trivial Hermitian operators because every complex Banach space admits Hermitian operators, at least those that are trivial, real multiples of the identity operator. One of such spaces is the space of continuously differentiable complex valued functions on the closed interval from 0 to 1. But we can also find spaces with non-trivial Hermitian operators. For example, any C-star algebra is such an example because Hermitian operators on a C-star algebra have the form X maps to AX plus XB for some self-adjoint A and B from the multiplier algebra of A. It is the largest C-star algebra, which is unital and contains A as an essential ideal. But in the case when A is a unital C-star algebra, it coincides with A. So you can think of these A and B as self-adjoint elements in A in that case. We shall be interested in Hermitian operators that are also projections. And by a projection on a complex Banach space, we mean a linear operator P such that P squared is P. And this definition implies that in general, P has the norm which is greater than or equal to 1 in general. There is a very useful characterization of Hermitian projections given by James Jamieson. A projection P on a complex Banach space X is a Hermitian projection if and only if P plus lambda times identity minus P is an isometry for all modulus 1 complex numbers lambda. And those spaces admitting only trivial Hermitian operators, real multiples of the identity, of course, admit only trivial Hermitian projections, 0 and the identity operator. But there are complex Banach spaces that admit non-trivial projections, Hermitian projections. For example, on a complex Hilbert space, every orthogonal projection is Hermitian. So this space admits plenty of Hermitian projections. Note that this characterization by Jamieson directly implies that if P is a Hermitian projection, then its complementary projection identity minus P is also Hermitian. And this characterization tells us that P plus lambda times I minus P, if P is a Hermitian projection, is always an isometry for all modulus 1 complex numbers lambda. And if we put lambda is minus 1, then we have that 2P minus I is an isometry, that is of norm 1, which by the simple use of the triangle inequality implies that any Hermitian projection must have norm 1. But P Hermitian implies I minus P is Hermitian, so this projection also has norm 1. In other words, it is clear that any Hermitian projection is also a bicontractive projection. However, the converse does not hold. Here we have a counterexample. If we consider 2 by 2 complex matrices equipped with the spectral norm, then a projection sending a 2 by 2 complex matrix to the corresponding diagonal matrix is bicontractive, but not Hermitian because P plus imaginary unit times I minus P is not an isometry. What about the structure of Hermitian projections on some other complex Banach spaces? In particular, we are interested in operator spaces B of H, S of H, and A of H. If P is a Hermitian projection on B of H, then P has the form X maps to QX or X maps to XQ for some self-adjoint projection Q in B of H. The space of symmetric operators admits only trivial Hermitian projections, that is 0 and the identity operator. But surprisingly, the space of antisymmetric operators admits non-trivial Hermitian projections. More precisely, P, if P is a Hermitian projection, then P or its complementary projection I minus P has the form X maps to QX plus XQ transposed for a rank 1 self-adjoint projection Q. And again, JB star triples allow a very nice description of bicontractive projections via isometries. Namely, this result by Friedman and Russo from the 1980s tells us that every bicontractive projection is the average of the identity with an isometric reflection. In other words, this result can be also rephrased that in the form that any bicontractive projection on a JB star triple is an Eigen projection of an isometry that has 2-point spectrum consisting of 1 and -1. And this motivates us to introduce a new class of projections besides Hermitian and bicontractive projections. And this new class generalizes the concept of orthogonal projections from the Hilbert space setting to the Banach space setting. And therefore, it is called the class of generalized orthogonal projections. A projection P on a complex Banach space X is called a generalized orthogonal projection if P and I minus P are the Eigen projections of an isometry with 2-point spectrum consisting of 1 and -1, such that P is associated to the eigenvalue 1 and I minus P to -1. By this definition, a generalized orthogonal projection is the average of the identity with an isometric reflection. And this implies that all generalized orthogonal projections must be bicontractive projections. And the result from the previous slide tells us that although in general it is not true, in JB star triples, these two classes, the class of bicontractive projections and the class of generalized orthogonal projections, coincide. And now there is the main problem that I have been interested in during the last few years. And the problem is the following. Where is a given finite set of modulus 1 complex numbers the spectrum of a linear isometry on a complex Banach space? This problem can be considered as an inverse eigenvalue problem for isometries. But first, let us see what can be said about the spectrum of a linear isometry in general. If it is surjective, then its spectrum is contained in the complex unit circle. If a linear isometry is not surjective, then its spectrum is the whole closed unit disk. So this answers the question why we are interested in surjective linear isometries, because we are interested in isometries having finite number of elements in the spectrum. Such an isometry must be a surjective one. Let us start with this result by Keller and Rosenthal that tells us that every isolated point in the spectrum of a surjective linear isometry must be an eigenvalue of that isometry with a complemented eigenspace. The assumption that our map is isometric cannot be omitted, because in general, it is not true that every isolated point of an operator must be an eigenvalue of that operator. Here we have an example. The Volterra operator has only one element in its spectrum, but this element is not an eigenvalue of the Volterra element, of the Volterra operator. But we are interested in isometries, so we have only eigenvalues in the spectrum. Let us now assume that we have a linear isometry with the finite spectrum. Let us say that its spectrum consists of lambda 1 to lambda n. By Keller and Rosenthal, every lambda I is an eigenvalue of our isometry T. Let us denote by Pi the projection onto the kernel of T minus lambda I times the identity operator, the so-called Eigen projection. Then all these Eigen projections are mutually orthogonal in the sense that their product is 0 and they sum up to the identity operator. Furthermore, the following spectral decomposition of T holds. T is lambda 1 P1 plus etc. plus lambda n Pn. And it can be derived that all these Eigen projections have norm 1, that is, they are contractive projections. But if T has 2-point spectrum, then it has 2 Eigen projections which are complemented to each other. Since they both have norm 1, they are both bicontractive projections. We should mention here that we can always assume, and we will, that one of these eigenvalues is 1. If not, we multiply our linear isometry with the conjugate of one of the eigenvalues. So in this way, we can get 1 as an eigenvalue. We should be interested in periodic linear isometries. A linear operator T is said to be periodic of period M if T to the power of M is the identity operator and T to any power less than M is not the identity operator. And there is a general result on linear isometries with 2-point spectrum consisting of 1 and lambda. It turns out that every such isometry must be periodic, or its eigenprojections are Hermitian operators. Periodic here means that this lambda must be some mth root of unity. But we also have a kind of a converse, because for any integer m, which is at least 2, and for any mth root of unity, there is a complex Banach space X and an isometry T on X such that its spectrum consists of 1 and lambda. That is, T has period M. But it turns out, and it is a very interesting fact, that in many complex Banach spaces, this lambda must be -1. In fact, we don't know any classical Banach space in which this lambda is some other mth root of unity besides the square root. Here we have some examples illustrating this fact. We consider n by n complex matrices equipped with a unitarily invariant norm, n by n complex matrices equipped with a unitary congruence invariant norm, and n by n complex Q-symmetric matrices also equipped with a unitary congruence invariant norm. I emphasize once again that we always assume that it is not a multiple of the inner product that is Frobenius norm. If we have a linear isometry on any of these spaces that has 2-point spectrum consisting of 1 and lambda, then lambda is -1, or the associated eigenprojections are Hermitian. But you probably notice that here in the symmetric case, we don't have this second possibility that the eigenprojections are Hermitian. And the reason for that is that on the space of symmetric matrices, we have only trivial Hermitian projections, 0 and the identity, and they cannot appear as eigenprojections of a 2-point spectrum isometry. We can consider also minimal norm ideals in B of H or JB star triples. Again, any linear isometry with 2-point spectrum 1 and lambda is such that lambda is -1, or the associated eigenprojections are Hermitian. That general result concerning JB star triples from the previous slide can be, of course, applied to C star algebras, and in particular commutative C star algebras, C0 of omega. But it was even before the general result observed by Fernanda Botelho that again, if T is a linear isometry on C naught of omega with 2-point spectrum 1 and lambda, then lambda must be -1. Again, we don't have the possibility that both eigenprojections are Hermitian, because here C naught of omega admits only trivial Hermitian projections. But here we notice something more. Namely, we have an explicit description of the eigenprojection associated to the eigenvalue 1. We know that when the spectrum consists of 1 and -1, then this eigenprojection P associated to the eigenvalue 1, that is the corresponding generalized orthogonal projection, is the average of the identity with an isometric reflection. That is isometry. Here we have a general form of the isometry as comes from the Banach-Stone theorem, but we also know that the square of this isometry must be the identity operator, which allows us to get some additional conditions on the homeomorphism phi and the unimodular complex valued function u. Of course, it can be done, and in fact, it was done in all the previous spaces, in all the previous spaces that I have mentioned on my slides. However, the corresponding papers were focused on the structure of projections, and here our focus is on the spectrum of an isometry, not on, it is not so important which types of projections we have here. And from now on, we shall assume that a complex Banach space X has the following property. If T is a linear isometry on X having 2-point spectrum consisting of 1 and lambda, then lambda must be -1, or both eigenprojections of T are Hermitian. We have just seen many examples of such spaces. And here comes the main theorem in this talk, obtained jointly by Fernanda Botelho and me. It concerns complex Banach spaces having the property that we called SP2 from the previous slide. This result concerns periodic linear isometries. And let us assume that our isometry T has period M and spectrum consisting of lambda 1 to lambda n. Let us denote by Ni the order of the eigenvalue lambda I. And let us denote by Mi the least common multiple of all orders except order of lambda I. Then one of the following holds. T has a Hermitian eigenprojection. Or all these least common multiples are mutually equal and equal to the period of T. Or they are all equal and equal to the period of T, except one of them, which is 1/2 of the period of T. In that case, the eigenprojection associated to the corresponding eigenvalue lambda j must be generalized orthogonal. We know that in some spaces, this first conclusion cannot happen. This is the case if the space admits only trivial Hermitian projections. But why is this a separate condition? Well, it's a long story, but I would like to say that having a Hermitian eigenprojection, in fact, allows that an eigenvalues somehow can become very wild. So we cannot find any nice connection between them in that case. But if an isometry does not have a Hermitian eigenprojection, then we have these two possibilities. But these two possibilities can be reduced to one of them. Because if 3 holds, then we multiply T by the conjugate of lambda j, and we get another periodic linear isometry of the same period M, but which satisfies. So this is a general theorem. What can be derived from it? The first natural step is to consider what happens with 3-point spectrum isometries when we have the spectrum consisting of 1, lambda 1, and lambda 2. Then one of the following holds. First possibility is that all Eigen projections are Hermitian. This differs from the main theorem, in which the first possibility is that at least one of the Eigen projections is Hermitian. But this conclusion, the conclusion of the type all Eigen projections are Hermitian, can happen only when we have 3-point spectrum isometries. Even when we have a 4-point spectrum isometry, this conclusion is not true in general, that all Eigen projections must be Hermitian. We have a counterexample. Or we are interested in the remaining 3 possibilities. Lambda 1 and lambda 2 have the same order, or order of one of them is 2 times order of another one. Can we say more about the eigenvalues that can appear? Without loss of generality, we can assume that our periodic linear isometry has period p to the power of alpha for some prime p and positive integer alpha. It is sufficient to consider t to the power of m over p to the power of alpha to get such an isometry. We assume for simplicity that none of the Eigen projections is Hermitian. If p is odd, then we know that at least 2 eigenvalues of t must have maximal order, p to the power of alpha. If p is 2, then of course the same can hold, but we also have another possibility because of our case 3, that precisely one eigenvalue has maximal order 2 to the power of alpha, and at least one has order half of it, that is 2 to the power of alpha minus 1. So maybe it would be nice to consider periodic linear isometries of some simple period, in a sense. So let us consider those of period 6, because 6 is 2 times 3. We assume that one eigenvalue is 1, which can we always assume, and we assume that none of the Eigen projections is Hermitian, which is here only for simplicity. Since we have a periodic linear isometry of period 6, it can have 3, 4, 5, or 6 eigenvalues. And here beta denotes the primitive cubic root of unity. So what we really have here? Let us consider 3-point spectrum isometries. It seems that we have 3 possibilities, but these in fact reduce to only one of them. Let us say that this first one is the main one, because the remaining 2 can be obtained from this first one by multiplying this set by the conjugates of these 2 eigenvalues that are not 1. The same holds when we have 4-point spectrum isometries for the first 4 sets. This is one case, but there is also another case consisting of the other 4 sets. So the first 4 can be reduced, let us say, to this one, and the second 4 can be reduced to this case. The same holds when we have 5-point spectrum isometries of period 6. We have one which is the main one, and remainings that can be deduced from the main one. But you probably notice that maybe we should have 4 remainings, and not only 3. But if we multiply the elements of this set by the conjugates of these 4 eigenvalues, in one of these cases we cannot get 1 as an eigenvalue, so there is a 1 case less, 1 set less. And here, if we have 6 elements in the spectrum, then the only possibility that it is the complete set of 6 roots of unity. The next question is if these cases can really happen in some concrete complex Banach space. We know that some of them can happen in C0 of omega. For example, this 4-point spectrum, the first one, a 5-point spectrum, and 6-point spectrum. We also know that the remaining 4-point spectrum case and 3-point spectrum case of period 6 cannot happen in C0 of omega. But we still don't know if they can happen in some other complex Banach spaces, and I think it is an interesting question. It would be nice to find such an example if it exists. And we shall illustrate what has been just said about such periodic linear isometries. First of all, we show that the complete set of 6 roots of unity can happen. We show even more that the complete set of nth root of unity can happen. Here we have such an example. What about 3-point spectrum isometries on C0 of omega? It turns out that, that such an isometry must be of period 3. That is, its spectrum consists of the complete set of cubic roots of unity. It was first observed by Abu Bakr and Dutta, but it is also obtained as a corollary of a more general result by Wong Liu and me, which is still in progress. So it shows also that we cannot get a 3-point spectrum isometry of period 6 on C0 of omega. What about 4-point spectrum isometries of period 6? We shall show that such exist, at least one of those 2 cases that I have mentioned. We define the set omega to be the union of these sets A and B. We define phi to be of period 3 on A and of period 2 on B. So phi has period 6. Therefore, the corresponding composition operator, which is a surjective linear isometry of C of omega, also has period 6, and it has 4 eigenvalues, 1, -1, beta, and beta squared. Here, beta also denotes the primitive cubic root of unity. Let us see how this result fits into the main theorem by Fernanda Botelho and me. We consider periods. First, we consider orders of these eigenvalues. These are respectively 1, 2, 3, and 3. Then we define those MIs, which are obtained by omitting one of the eigenvalues and considering the least common multiple of the orders of the remaining ones. If we cross this one, then the least common multiple of 2 and 3 is 6. So M0 is 6. If we cross this one, then we have 1 and 3. So M1 is 3. If we cross this one, these have orders 1, 2, and 3. So M2 is also 6, as well as M3. So we have respectively 6, 3, 6, 6, which is the third case from our main theorem, because all these least common multiples are equal to the period, that is 6, and one of them is half of it, that is 3. And this is the spectral decomposition of T. Let us note that if we consider T to the power of 3, then we get P0 minus P1 plus P2 plus P3. So it has eigenvalues 1 and -1, and therefore T to the power 3 is generalized orthogonal. P1 is generalized orthogonal, and T has 2-point spectrum. Its Eigen projections are P1 and identity minus P1. What about 4-point spectrum isometries of C0 of omega? These are the only cases that can happen. The complete set of fourth root of unity, it can happen. Any complete set can happen. We saw an example. Then this 1 minus 1 beta and beta squared, it can also happen. We have just seen that example. And the remaining 3 can obtain from this one. So all these cases can happen in C0 of omega. What about 5-point spectrum in general on C0 of omega? Such spectrum can only be one of the following. The complete set of fifth roots of unity, it can happen. Then this set and the remaining 3 can be obtained from this second one, which can be considered as the main one. We shall see that this can also happen, and therefore the remaining 3 cases. But if u is a constant function, that only this first case is allowed. It means that in our example, we are going to have really a weighted composition operator, not only a composition operator. This example looks complicated, but we shall see the picture that will explain everything. Omega is the union of these 5 sets, A1, A2, A3, B, and C. Phi is defined to have period 3 on the union of A1, A2, and A3, and to be of period 2 on the union of B and C. So phi has period 6. Here we also define the corresponding weights, and I would like to emphasize that the weights are constant on B, it is 1, and on C, it is the primitive cubic root of unity. The corresponding weighted composition operator has period 6 because phi has period 6. And now we can see our space omega. The north and the south pole are fixed for omega, fixed for phi. So in order to get the corresponding eigenvalue, we simply take u of omega, which is 1 for the north pole and beta for the south pole. Now we exclude the poles and we consider A1, A2, and A3. Phi has period 3 on these 3 sets. So we calculate u of omega times u of phi of omega times u of phi squared of omega. It is 1. Then we take square roots, cubic roots, and in this way we get this first set of eigenvalues, the complete set of cubic roots of unity. On B and C, phi has period 2. So we calculate u of omega times u of phi of omega, and we take square roots. This product is 1 on B and beta squared on C. So B gives us this second set of eigenvalues, and C gives us this third set of eigenvalues. And in fact, we get the set of eigenvalues that also appears in the corollary by Fernanda Botelho and me. In the case when we consider periodic isometries on continuous functions on the closed interval from 0 to 1, then the only possibilities are that the spectrum consists of 1 point or 2 points with sum equal to 0. So if one eigenvalue is 1, the other one must be minus 1. In this case, we cannot get 3, 4, or more elements in the spectrum. We can also mention 3-point spectrum isometries on minimal norm ideals. Then the associated Eigen projections are Hermitian, or lambda 1 and lambda 2 are related in the following way. One of them is the conjugate of another, or one of them is the square of another. And when we compare that with the corollary by Fernanda Botelho and me, we noticed that, we recall that our conclusion was that lambda 1 and lambda 2 have the same order, or order of one of them is 2 times order of another one. There is a general theorem for JB star triples and finite spectrum isometries. We have two possibilities. One of them is maybe too strong when comparing with results by Fernanda Botelho and me. We had one of the Eigen projections, at least one is Hermitian, but here all Eigen projections are Hermitian. And therefore, the second possibility is maybe too weak. It gives us some relation between the eigenvalues. Namely, they exist I, J, and K. K is not equal to I and not equal to J, such that lambda I times lambda J times the conjugate of lambda K is one of the eigenvalues. It can be useful only when n is a small number. Let us say in the case when we have 3 eigenvalues. Then we have the same conclusion as for minimal norm ideals. And finally, I would like to present some of the recent results. I'm going to approach to the end very soon. It concerns unitarily invariant norms on n by n complex matrices. It turns out that for isometries of the form x maps to uxv, we can get any element in this, any number of elements in the spectrum, any number of eigenvalues from 2, the minimal one, to n squared, which is the maximal one. But for isometries that are of the type x maps to ux transposed v, it is not the case, because we cannot get 3 or 7 eigenvalues. And for 4 by 4 matrices, we cannot get 11 eigenvalues. All other cases can appear. On n by n complex symmetric matrices equipped with the unitary congruence invariant norms, all number of eigenvalues can appear, from the minimal one 2 to the maximal one 1/2 of n times n plus 1. The same holds for skew symmetric matrices, except, again, in the case when we consider 4 by 4 complex matrices and isometries of the form x maps to gamma. Recall that it concerns interchanging some entries of uxu transposed. In that case, we can get only 2, 3, and 4 elements in the spectrum and not 5 and 6. And now it is clear that the main result by Fernanda Botelho and me gives us necessary conditions on a finite set of modulus 1 complex numbers to be the spectrum of some isometry that has finite spectrum. But for sufficient conditions, we have to restrict our study to some particular spaces. And what is next? I would like to see more concrete examples and counterexamples that illustrate our main theorem. Thank you very much for your attention.
What a I just can't describe to you how much I enjoy. It was completely engrossing and just amazing. Already Ajitji made that comment in the chat box.
Thank you. Thank you so much. Thank you.
Amazing, Dijana. And thank you, Fernanda also is here. So it was so exciting to see both of you together. So anyone, any questions, please? I am completely, it's like watching a film. It was just absolutely amazing. Yeah, any questions, anyone? Or comments? Anyone?
You see, people usually associate the word unitary or Hermitian with Hilbert space operators. But for Banach space, very systematically, the whole theory has been developed by Diana and Fernanda and TSS and others. And it is very interesting to watch it flow so smoothly.
Yes.
Yes, yes, that's true. Yes.
Absolutely fascinating, Diana. Thank you so much. Anyone, any questions, comments? If not, then I'll ask Stefan to make a few concluding remarks.
Yeah, I would like to thank you very much for this excellent talk.
Thank you.
And yeah, maybe if anyone has questions after the talk.
Yeah, one more thing, if I don't, I just want, if you could share your slides with us, Dijana,
Yeah.
it would be great.
You want me to send you slides? Yes,
you-
yes, of course. No problems at all.
Thank you.
Yeah. I
And
think
we'll
maybe
also put it on the YouTube so people can watch it again. So
Okay, thank you.
maybe if any questions come up, they could also be asked by email.
right, exactly. This was just fascinating.
So,